Okay, so starting off from where we left off in the last class, this momentum flux at at position R and T. So what we could talk, and this is from Rife section 13.1, momentum flux at R and T across dA, right? Which is also can be interpreted as pressure in dA, is nRT, number density of particles, into m, into this is n hat vector, the unit vector perpendicular normal to the area, into ui, where this ui is basically the fluctuation of the velocity about the mean velocity ui, into mvx, and this is the so-called average taken over all different velocity vectors. Now, if you could take n to be z hat, suppose suppose the fluid, the velocity, the mean fluid velocity, the mean velocity O of that volume element d3r was in the x direction, and suppose n hat is taken to be z direction. Let's take that to the case 1. Then the pzx, the momentum flux, and the so the momentum flux, the area is the normal to the area is along the z direction, and what you are interested to calculate is the momentum flux of the z, the momentum flow z direction across x, right? So even as gas particles are moving along this, so are moving, suppose, in this direction, so this direction, so they have some x component of the velocity, as hence they are crossing this area A, right? But the question is how much momentum in the z direction is being transported as a consequence of a particle going from this point in space to this point in space, ui dt, right? So that's the thing which we are calculating, and that is essentially nm mass into uiz, right? And that is ui, this is the fluctuation. This is the fluctuation of the velocity plus u bar, right? So that amount of momentum is getting transported in the z direction, if you like. Right. And this average is over small slices of time over all particles in a unit time. So this slice of time, this unit time, is a small slice of time, but it is much larger than the collision time, right? And then if you basically so then the term that you get, so if you open up the brackets, you get uzi uxi plus u bar into uix, and this is the so-called fluctuation. I think this should be z actually. Yes, you are opening this up in the z, but in the z direction there's no net momentum. So when you take an average, this will get to 0, and even if there was this, you are really writing down the fluctuations, right? This would get to 0, and what you would get is the net momentum transport due to collisions or the motion is uzi uxi. Similarly, if you took so if you took both to be in the z direction, then you would get nm uiz ui z. So here the area is taken along the z direction, and this would basically correspond to the local pressure. And note that this local pressure, when you are taking, you are really averaging over the fluctuations about the mean velocity, right? Even if there was a mean velocity, I mean, it would not contribute, and all the pressure, I mean, this, in that case, this would get to zero, and I mean, this is the fluctuations. That's what decides the pressure, local pressure. That's due to small volume particles interchanging positions, and you are averaging over all values of the velocity vector. That's what it means. So keep this in mind. You could also calculate pxx, and then this would be x, and then this again would be x, right? And this quantity would give 0. So this is all that you will have. This is about the uh, so some particles are moving to the top, some particles are moving to the right, and this is about the mean velocity that you are calculating the pressure, right? Uh, Next, let's talk about the evolution of distribution function in absence of collision. Okay, so there's an ideal case. Of course, in reality, there is always a collision, and the collisions actually try to bring the distribution function closer to back to equilibrium, right? And let's assume that there is some conservative force field, let's say electric field, external electric field, but let's call it F. You know, but it can be this F can be E into electric field capital E, E being the charge, or Q into E also you could consider this. So presence of a conservative force field. Uh, and what we are writing is doing a Taylor expansion of the position. dt is small, but much larger than the collision times. So uh, R dash at a different point in time is the position at time t plus r dot dr dt, if you like. So we're doing a Taylor expansion into d, and this r dot is v, and we are ignoring higher order terms, right? So dt is small enough so that we ignore higher order terms. And similarly, v dash at a later point in time can be written as the velocity at time t plus v dot into t, and this v dot is the acceleration, and which is force by m. Right now, it can be shown, and it has been shown in section RIFE 13.2.5 that so if you can consider d3 r dash and d3 v dash for small values of time, and if you're ignoring terms order of t square, then d3 dash, the unit volume in the 6D space, is equal to d3r d3v. And basically what we are doing here is calculate dx dv, and just multiply it into then calculate dx into dy into dz. And if you, right, and do that for r dash and v dash, and when you multiply, what you'll see that the Jacobian is 1 plus terms order of t square. And if you want to see the proof, this is where you can find it. And the point is, this volume element d3r dash d3v dash, which is equal to d3r d3v, that is not changing as a function of time. And hence what you could write that the in the absence of collisions, this is what I'm writing, in absence of collisions, then whatever particle is moving in whichever direction, it keeps on moving. There is no redistribution. The f dash, because there is no change due to collisions, it keeps on. So what you get is f dash r dash v dash t at time t dash. So this unit volume would have moved somewhere from position r and v to r dash and v dash at a later time t dash. But this volume element also in 6D space would have also moved, but this doesn't change, right? Because the same distribution function in different directions just moves from here to there. Uh, but this is in 6D space, so note that v and v dash have become so v has become v dash. So if there's an acceleration, they're just going to move in the velocity space as well, right? And since these two d3r and d3v is equal to d3r dash and d3v dash, what you get is f dash equal to f in the absence of collisions and for small time. So basically it is unchanging, uh, it's nearly unchanged with respect uh, as the distribution function flows uh, over over space and time and so on and so forth, right? Uh, so what you could write is f dash minus f is equal to 0 because this is unchanged. And then what you do is write f in terms of r and v, this one, and del f del x, x dot dt, del f del y, y dot dt, plus other terms, right, corresponding to v and so on and so forth, minus this term equal to 0. The consequences, this term and this term cancels, and the Boltzmann that equation that you get in the absence of collision is del f del x, change of f in the x direction, in the y direction, uh, uh, right, and z direction, and similarly in the del b del x and del b del fy, this dt equal to 0. So this Boltzmann equation you write in as capital D into F equal to 0. So Boltzmann, this is the so-called Boltzmann equation in the absence of collision. So there's a continuous flow of the distribution function in x space and v space without uh, any change, because the phase space volume is not changing, order of ignoring terms, order of t square. So this is the meaning of this. It's just unchanged, but in reality you do have collisions. So as the distribution function explicitly does change, so there is, remember here there is some flow, but this is the explicit, the sum of this and this equal to 0, right? But in reality, what happens is there are collisions. So there is an explicit time dependence in f because of collisions part in a small time interval dt. The number of particles which are moving in v directions, say in a particular v directions, actually changes, right? Because some particles were moving due to collisions, they start moving in different directions. However small, I mean, you are considering a time which is small but large enough. There have been multiple collisions which have taken place, and what Boltzmann assumed is that the effect of collisions is just to take the system. So there's an assumption, and you say that the effect of the collision is just to take the distribution function towards the so-called equilibrium distribution function. Okay. So what I said is in reality that there are collisions, momentum energy, momentum energy mass is transported, and due to collisions, densities become homogeneous unless maintained by an external driving. So in reality, thereby what you should write is not df equal to 0, where everything keeps on moving in the same direction in the x and v space, but uh, this thing, the distribution function, will change, and it will change explicitly as a function of time in a small interval dt, and they will be due to collisions. So in the presence of collisions, and this is right section 13.6, the distribution function right at r dot plus r plus r dot dt, v plus v dot dt, and at time t plus dt will be the original distribution function plus a change due to collisions, which we write as df del f del t, an explicit dependence in time which does not depend upon r and v due to collisions. So here I mean, as I already said, Boltzmann assumed that the effect of collisions is to restore local equilibrium at R and V, uh, to, to get it back to the equilibrium distribution. The equilibrium distribution is denoted by F0, right? So suppose there's an equilibrium distribution and any deviation from equilibrium distribution is small. That's another assumption. And then in that case, the simplest assumption to take is the way that there is a single relaxation time for that, for the gas molecules to reach equilibrium, and DCF, the effect of collisions, is to take back the distribution F to F0 in a relaxation time, and a single relaxation time tau 0. Now, where does this tau 0 come? It has to come due to collisions, and the effect of multiple collisions is absorbed in a single relaxation time tau 0. Of course, the question is how will you get tau 0? But let's assume you have a value of the tau 0. Somehow you know what is the relaxation time of the entire system. Then let's see where we can proceed. And what this says is the effect of collisions depends upon the difference of distribution functions, and that relaxes to the equilibrium one, to the equilibrium. So the distribution function relaxes to the equilibrium distribution function F0 in a time tau 0, and there's only a single relaxation time approximation. So why does that? So one could write that df dt essentially is equal to minus f minus f0 by tau, right? The rate of change of f depends like this, and this can be integrated basically df by f minus f0. When you integrate it log f minus f0, you get minus t by tau 0, right? We're integrating, taking t on the right hand side of the equation. We are taking dt to the right of the side of the equation and integrating plus ln c. So now at time t equal to 0, you assume, you say that so at t equal to t0, you assume that it was at whatever be the distribution function, call it f minus f0, or rather I think at t equal to 0, you would get ln c equal to ln f0, the distribution function at time 0, minus the equilibrium distribution function, right? Yes, you would get this. I have mixed ln here. So so when you incorporate that and you bring ln c to the left hand side of the equation, ln f minus f0 into f0 minus f at time 0 minus the equilibrium distribution equal to minus t by tau 0. So you would get f minus f0 equal to this constant term into e to the power minus t by tau 0. Now, what does that mean? So, at time t equal to 0, suppose there was a difference between the distribution function and the equilibrium distribution function, and this difference was this quantity. Then, at time t, the distribution function would become f0 plus this quantity. And what is this quantity? This quantity is going to decay with time, going to exponentially decay with time, right? Because this term is going to decay at times greater than tau 0. This is extremely small. So at times much larger than tau 0, left to itself, the distribution function would become f0 at I mean any time beyond tau 0. So by writing the effect of collision in this manner, it says that the equilibrium, that any distribution function as a consequence of collisions which are being modeled by this expression, the effect of collision is modeled by this expression. The consequence is that the distribution function will decay to the equilibrium distribution function in time tau 0. So the effect of collisions is to take the distribution function back towards the equilibrium distribution. And in general, the Boltzmann transport equation then can be written in a very small manner as df, which is looking at the flow of f in x and v and also t. So how is it moving as the particles move, and that is equal to dcf. And though this looks very small, actually this has to be written as del f del t plus v dot del f. So the vx into del f del x, vy into del f del y, and so on and so forth. And similarly here, force by m, fx by m into del f del vx, fy by m into del f del vy, and so on and so forth, minus f0 by tau 0. Right? Now, to study this using the simplest approximation, the so-called exponential singular relaxation time approximation, which says that any distribution function is going to basically relax to equilibrium values in time tau 0. So if so if f is, so note that if f is equal to f0, dcf is equal to 0, because because this term is going to become 0, right? So if it is remaining, if f is already, if the distribution function is already the equilibrium distribution function, then there is nothing for this to this is nothing for it to decay to. It is already at f0. This will be 0, and then again you will have the general distribution function, the df equal to 0, right? Yeah. But remember, I mean, if there is no external field, then this f by m equal to 0, right? So basically, the distribution function will move around in space, but there is also no del f del r, because all over it is uniform, right? It is uniform all over space, because if it is reached equilibrium. right? So then there won't be any relaxation. There is no explicit time dependence of the distribution function in terms of time. But if there was such a thing, in case there was an electric field which is constantly driving F away from its equilibrium value, right? It is driving F by m is drive as the particles move, they're getting accelerated, they're moving uh, up in the velocity space, they are speeding up, then that would be continuously. So there is an external driving, there's an external force, means there's an external driving. And then locally, the effect of these collisions will be try to bring it back to the equilibrium distribution, right? Now, when there is an electric field, say, right? So suppose Fz by m is equal to the electric field, and further, let's assume that there is no explicit dependence of F in the on real space. So there is uniform density, relatively uniform density, and all that this electric field is doing is drive the distribution function up in the velocity field space, right? And the effect of collisions is to try to bring it back, because so suppose something is accelerating, it has picked up velocity, but that it collides with another particle moving in another direction, and its effect is to bring it back to the equilibrium distribution, and all of it is subsumed or is absorbed. The effect of collisions is absorbed in a term which looks like this. Then let's see whether we can calculate the transport coefficient conductivity. So what is this system? This is a system which is constantly being driven by the electric field. So F is constantly changing, and due to collisions coming back to the equilibrium distribution. Hence, there will be some steady state reached all over space. There's a net current, and so it's constantly accelerating and being brought back towards the equilibrium distribution as a consequence of collisions. And what is the effect? What is the net current that the net flux of charge? Let's try to calculate that. So what we are assuming is FRVT is steady state, so there is independent of space and time. But F of V has an explicit dependence on velocity, because del F del T equal to 0. This is equal to 0. There's no explicit dependence on what is it called? On space, but because there's a force, this term actually contributes, because in the velocity space, this is constantly, F is evolving and increasing. I mean, higher velocities are increasingly being occupied due to the effect of the electric field. Now, here we also assume that the F0, this is a separate calculation, but I'm just trying to absorb. So this is another proof. It will go off in another direction, but I'm just bringing it back. So let's assume that F0 with no explicit dependence in R and T is equal to, can be written as GV, and that is the Maxwell-Boltzmann distribution of speed, right? So in equilibrium, the Maxwell-Boltzmann distribution of speed is well, it can be shown also, but I'm asking you to assume it. And the Maxwell-Boltzmann speed distribution is n m beta. Beta is 1 by kbt. So this beta, it will contribute a kbt in the denominator, the 2 pi into e to the power minus beta v square, vx square plus vy square plus vz square into m by 2. And this quantity can also be written as e to the power minus beta e, which you know from your statistical mechanics, right? Now, note in the energy, we are not considering potential expression for the potential energy. So we are assuming that interaction between electrons is neglected, right? So all the energy is kinetic energy. That is possible if the electrons have such high velocities, the contribution to the potential energy, the contribution from the potential energy is negligible. So that's the assumption which is going on. So though we just wrote down the Boltzmann, well, this is the equilibrium distribution, but you're considering charged particles. So there should be an interaction, but we're neglecting that. We're saying that the particles are moving with such high velocities that the potential energy is not contributing to the total expression for energy. In general, n beta u, these can be functions of r and t, but we are not considering that. At the moment, we are trying to keep it simple. And in that case, the Boltzmann equation, what you will get is Q, I mean, the charge of an electron into the electric field by m. And suppose it has been, the field has been applied in the z direction, then del f del v z. And that is equal to F1. F1 is F minus F0 is named F1. I don't know. Yeah, here I had named F minus F0 is F1. And we have assumed that the difference, this difference of the distribution function in non-equilibrium, F minus F0 is small. F1 is smaller, much smaller than F0. So this becomes the Boltzmann equation, right? And so assuming that E is small, then basically the increase in velocity of the particles, suppose in the z direction, if E is applied in the z direction, the change in the velocity in time t or in time tau, the time of the relaxation time, the change in velocity in time tau is much smaller than Vz. It has been accelerated only slightly, and then it is being brought back to equilibrium. That's the assumption which is going on here. And F can be written as the equilibrium distribution plus F1. The deviation from the equilibrium distribution is F1. And as a consequence, del F del Vz, so this quantity is del G del Vz, the change in the equilibrium distribution in the direction of Vz, del G del Vz, plus del F1 del Vz. And since F1 itself is a very small quantity, and then there would be even a smaller change, right, due to the acceleration, due to the electric field, right? So this is a small quantity. And then this is likely to be a small quantity. This is a small quantity because F1 itself is a small quantity. Now, how much will it change with Vz? So it's very small. Hence, what we can write, so when we are writing del F del Vz, we are approximating it as del G del Vz and ignoring this term. So what we have written here is F1, and if we take tau 0 on the left hand side of the equation, so then F1 equal to minus E, I mean, so it is this minus sign E into E. I mean, of course, E can come with a negative sign itself. That's just the charge, but we are writing it as the charge E, right? Into the electric field tau 0 M del G del Z X. Now, all that we are doing is do a transfer of variables, because GV can be also written in terms of e to the power minus beta E, right? So we can do that. So what we are doing here is essentially del G del Vz is being written as del G del E into del E del Vz, and when you calculate del E del Vz, and it's being calculated here, that gives mvz. As a consequence, del G del Vz becomes del G del E into mvz, and then you have all the other terms sitting here, right? So this m and this m cancels, hence you don't see a m in this expression. Now what happens? So the right, so now you have an expression for f1 in terms of del G del E. How does G change with the energy? And other than that, you have these terms sitting here. Now, as we wrote down, if you wanted to calculate total flux of the charge, let's call it J, then that is equal to E into d3v f Vn, because Q, so Vn is the flow of particles, right, and into E. Now suppose n hat, right, equal to the z direction, but we have written f1 is this term. I have written this. So when we are calculating the flux, right, when we are calculating the flux, we can write this as so what is the conductivity? The conductivity is flux per electric field. That's the flux, amount of charge carried per unit area per unit time into the electric field. This can be, so this electric field has come here, so that you have is E d3v. Now if there's the equilibrium distribution, then an equal number of particles are moving to the plus z direction and the minus z direction. So that is not going to contribute to the charge flux. What is going to contribute to the charge flux? Only the non-equilibrium part, which is F1, right? And that we have substituted here. So E d3v, F0 or G doesn't contribute, and all that we have is F1. So you have E tau 0 Vz del G del E, and from here this Vn is Vz here. Now we have to calculate del G del E. Now G is equal to this quantity, the equilibrium distribution of the equilibrium distribution function, right? When you take a derivative with respect to G, these terms remain intact, and all that you get is an extra minus beta when you tweak the del del E of e to the power minus beta E. So what you get is del G del E equal to beta G, right? In that case, the conductivity, which is J by E, becomes, I'm taking the tau out, E square beta, the beta came from here, right? And there was a minus sign here, and you got a minus sign from here, del G, from del G del E, that gives minus beta G. So hence you get a positive, and hence you get a positive, where do you get? So there was a minus sign here. This minus sign, by the way, came from here, this minus, and when you take the derivative, you get another minus sign. As a consequence, tau 0 E square beta integral over d3v G Vz square. But G, the distribution, the equilibrium distribution function, right? This is the distribution function, the equilibrium distribution function, into Vz square over all velocities is nothing but the mean Vz square, right? The average value of Vz square. And remember, we are using the equilibrium distribution function here, right? As a consequence, this Vz square is nothing but half kbt by m. And this n remains intact here, right? Now, you have a kbt here and 1 by kbt due to this term. As a consequence, so basically half mvz square would be half kbt, but if you have vz square average, then you wouldn't have the half here, you will just have n kbt by m, which you substitute, and kbt and this cancels, so you have tau, some average tau, the relaxation time, the average relaxation time due to collisions of all the gases, some tau, some time scale in the problem, E square n m, and beta has cancelled. So this is the so-called, under the approximation. So under the approximation, the charges are not interacting with each other. The effect of collision is to get back the system to equilibrium as quickly as possible, or in a time scale tau 0, there's a singular relaxation time. The conductivity will be this. Now let's apply this. We are talking about gas, but if we apply it to electrons in a metal, then this n will be the density of electrons in a metal which are contributing, which are colliding and contributing to the which are moving up in velocity space and contributing to the conductivity. And the effect of collisions is to bring it back. We are using relevant relaxation time tau 0, right? And so this is the so-called Rude model, and if you use this, you get an estimate of the electrical conductivity. Now remember that there are a certain number of electrons in the metal, but as you will soon later realize, or you might have realized in the condensed matter course, that you might have a large number of electrons, but only a few, very few electrons near the Fermi surface is what contributes, or which get accelerated, which can move to higher energy levels and get accelerated, change their V. So the density of electrons that you should, so the density of free electrons is what you should use, not density of electrons. Those are the ones which get accelerated and contribute to the conductivity. And so the n that you should use here is those, and that you can get the value of density of electrons which are contributing to the conductivity, that you can get from Hall measurements if you have done some. I mean, anyway, even if you have not done, I cannot put everything in one lecture, but this density of electrons is accessible to you, at least for semiconductors, in Hall measurements, right? And if you get that in a metal or in a semiconductor, then you know what is, to some approximations where we approximate a single relaxation time, where we neglected interaction between electrons, where we are assuming this to be a gas, we're neglecting the effect of the lattice, and so on and so forth. And we assumed, of course, that collision at each point in space, the electric field is perturbing the F, whereas collisions is trying to bring it back to the equilibrium distribution. Under such conditions, we essentially have an expression for the conductivity, which is a macroscopic quantity, in terms of microscopic quantities n, E square, m, and some relaxation time tau. Of course, the question is how will you get access to the relaxation time? But that's another discussion. But suppose you have this microscopic quantity tau 0, then you can express a transport coefficient like conductivity in terms of microscopic quantities. So this is the message, and we'll continue from the next lecture. So let's see. Yeah, so let me